Okay, this goofy looking scatter plot thing is what we call an NZ plot of stable nuclei. So NZ plot, and the N and the Z stand for neutrons and Z stands for protons, which is atomic number. The N goes on the y-axis. This is neutrons. The number of neutrons increases as we go up here. The symbol for neutrons is N with a little 0. Up there is an exponent, and then the Z is atomic number, which is the same thing as the number of protons. And proton symbol is P with a little plus sign right there. So the number of neutrons goes up as we go up, and the number of protons increases as we go to the right. What you see here is this big band of these colored boxes. Each colored box represents a stable nucleus, a stable combination of protons and neutrons. Stable means that it's going to stick together and be that particular atom, that nucleus is going to stick together for basically forever. And all of these boxes that aren't colored in are isotopes that can and oftentimes do exist, but they just aren't stable. They'll fall apart. They're what we call radioactive. And we get this big stripe, this kind of band through the middle of this chart where all of the stable ones occur, and we call this the band of stability or the region of stability. And there's some things that we should recognize about that. It looks pretty straight, but it's not perfectly straight. There's kind of a little kink in it. In fact, if we take this, let me erase what I just did there, the band of stability. I can leave that on there, I suppose, but erase this circle I drew. The band of stability is right there, and if you follow this line that's drawn in here, I drew this black line in there, and that's got a slope of 1, where the number of neutrons is equal to the number of protons everywhere along that line. The band of stability appears to line up right along that line until we get right about to there. That is element 20, and element number 20 is calcium. At calcium 20, or calcium 40 rather, there seems to be a break where this thing goes from having a slope of 1 to all of a sudden having a larger slope. And if we take and draw in a line here, that is a line of best fit for this portion of the graph, you can see that it's much steeper than 1. And so the rule of thumb that we have got for stability, if you had to make a guess, if you were asked to on a test, or if someone was walking down the street and decided to ask you if something was going to be stable, you would say, okay, if it's a small atom, smaller than calcium, if it has less than 20 protons, then the neutron to proton ratio for stability is got to be close to 1 to 1. 1 neutron for every 1 proton, an equal number of protons and neutrons for atoms that are small, less than the size of calcium. For atoms that are bigger than calcium size, for the ones that are up here in this upper region, larger than 20 protons, if you look at this carefully, it looks like we go over 10 squares and up 15 squares here about with this, so the slope is pretty close to 1.5. So, and for the region larger than calcium, the neutron to proton ratio to get stability is that you need 1.5 neutrons for every 1 proton. Now, we usually don't keep decimals in ratios, and so we'll multiply this by 2 and make it 3 to 2. So we need to have 3 neutrons for every 1 proton in order to have a stable atom if it's a bigger than calcium, if it's got more than 20 protons. That's kind of the rule of thumb that we use. Is it always going to be true? No. There's lots of little gaps in places. You could if you could have something with a perfect 3 to 2 ratio up in the upper region here, and it might be still be unstable. But if you had to guess, those are safe guesses. Okay, the next thing that we need to look at is these boxes that aren't filled in. All the colored boxes, again, represent stable nuclei. And so we have this region of stability, which is this band, this stripe that goes through here, where we've got all the stable ones in that area. What happens to atoms that aren't stable? The atoms that aren't stable are what we call radioactive, and they are going to decay. They're going to shoot out parts of themselves. It's called nuclear radiation, in order to try and become stable. So the very first one on your homework that you're asked to plot, in addition to these guys, was with Z equals 50, N equals 80. So if we count over to element 50, 1, 10, 20, 30, 40, 50, and up to 80, we get somewhere right in this neck of the woods right there. And element 50 is tin, And so if we write this in AXZ notation, 50, and then if it's got 80 neutrons, 50 plus 80 is 130. So tin 130 is the isotope we're talking about here. Tin 130, if we look at it, is above, it's over the top of the region of stability. It's got too many neutrons, it's too high. So if it wants to become stable, it needs to lose some neutrons. Or it could also, you could think about it in terms of protons, it could gain some protons and move to the right as well. So when it gives off nuclear radiation, when it tries to become stable, it's going to be losing neutrons and gaining protons in order to try and wiggle down into this region of stability. And when it changes into one of those stable isotopes, then it will stick like that forever. It'll stop being radioactive. It'll stop decaying. The next isotope that you're asked to plot was Z is 60 and N is 60. And so if we come up here and find 60, 10, 20, 30, 40, 50, 60, we are going to be right in that neck of the woods right there. That isotope, let's see here, element 60 is neodymium. So 60 protons is neodymium, and if it's got 60 neutrons, that means its mass number is going to be 120. So neodymium 120 is that green dot right there. And neodymium 120 is below the band of stability. It's got too few neutrons. And so when it decays, it's going to try and move up. It's going to try and gain neutrons, or also, and maybe both of these things, it'll try to lose protons. It's got too many protons. It's too far to the right of the band of stability and too far below it. So it's going to lose neutrons to move to the left and gain neutrons to move up, and then that way it's going to kind of wiggle itself back and forth up until it gets into this region of stability and it changes into a stable isotope, and it'll stick like that forever. The last one that you're asked to do is to do 87 protons and 129 neutrons. It puts you way up in the corner up here. This thing over here is a zoomed in portion of that top right corner of the graph here. I've made it big so we can see a little more clearly for some of the things we do. 87 protons is francium, and 129 neutrons means that we are talking about francium 87, and 129 plus 87 is 216. So francium 216 is our isotope in question. Francium 216 is up here. It's got both too many protons and too many neutrons. It's up and to the right of the band of stability. So it's basically just too big and needs to lose both protons and neutrons. So we can expect when we have this isotope, it's going to be radioactive, it's not stable, and it's going to be trying to lose both neutrons and also lose protons in order to move itself down and to the left and down and to the left, and hoping to eventually change into one of these stable isotopes, and then it will stay like that forever. So we're going to talk about this more when we talk about nuclear decay and writing decay reactions. But you can predict what kinds of radiation different isotopes will give off based on whether they need to gain protons or lose protons, gain neutrons or lose neutrons, in order to move into that band of stability. Their goal is to change into a stable isotope, and then they'll stick like that forever.